So welcome back. I'm Bill Langdon. I'm going to give the next talk, which is on deep mutations have little impact. Yeah. So this is joint work. Oh, okay. Better? So Bill Langdon, this is joint work with David Clark. We're both in the CREST lab at UCL. And the idea is okay. The idea is I'm going to talk about deep mutations have little impact. This is work extending Boas's pi framework. So I'll talk a little bit about how he views the propagation of software disruptions. We're going to extend it from just looking at software bugs to looking at disruptions in general. We're going to look at deep mutations in pure functions, particularly those generated by genetic programming. But what the talk is really about is looking at traditional imperative C++, which has got side effects, it's got global variables. And again, we see evidence that deep mutations tend to have little impact. The last experiment is taking Amric's Magpie system. He's going to give a tutorial after lunch on that, and essentially applying it to one of the parsec benchmarks. It's actually a small program which generates thumbnails. So given a large image, it generates a thumbnail image from it. And hopefully we'll have time to talk about some of the implications. So the idea of Boas's work was to say that for a bug, a software bug to have impact, it must not only exist and be executed, but it must also change the behavior of the program in some way. He called this infecting the program state. That infection, that change of state, must propagate to the output or to some print statement. What we've done is to generalize that to consider any form of disruption. So maybe the program got irradiated, maybe there's a transient error, maybe there's a power glitch, or in our case, maybe we've deliberately mutated the code. We view all those as types of disruption, and then consider, does that disruption propagate to the output? And we're looking at using information theory to explain cases where that disruption does not propagate to the output. Essentially, the code is robust to the transient. Maybe it's a mutation, maybe it's some other form of disruption. So the idea from information theory is all operations within a program are irreversible in the sense that we can't infer uniquely the inputs from the output. So here I have a simple addition. We're taking two 32-bit floating point numbers. They can contain at most 32 bits of information. So coming into our funnel, we have at most 64 bits of information. It generates a 32-bit output, though it can generate at most 32 bits of information. So the idea of the funnel is where all our operations are taking more information in than they're passing out. If we have a hierarchy of these, the information can only propagate up through the hierarchy. If information is lost, it cannot be recovered. So this is the case where the functional programs have this inbuilt irreversibility. Possibly in programs with side effects, you might be a way of going around this hierarchy. In the top, we've got 6 inputs shown with the arrows. The idea of the red arrow is that's supposed to indicate there's been some form of disruption. comes into one of our functions, and it gets progressively diluted. So at the output, we may not actually see that disruption at all. So there's one example where I can do the maths just to quantify information. So here we view information in terms of entropy. We're going to take a very simple case of uniformly distributed digits between 0 and 9. The mean is obviously 4.5. Standard deviation is the square root of 8.25. The entropy is log 2 of 10. If we add those together, then obviously their mean just increases in terms of how many things we add together. Their standard deviation increases as the square root of that number. If we have a large number, then the distribution as a whole tends to a Gaussian distribution. I'm going to skip the movie, but online there is a movie that shows you that the change from a uniform distribution into a Gaussian distribution. Gaussian distribution has a well-defined entropy. It's 2.047 plus log to the base 2 of the standard deviation. And the point of the little table is to show as we go from 1 input to 2 inputs to 3 inputs, the entropy off in the 4th column, that's the actual entropy of the distribution of adding those numbers together. And you can see it converges on the distribution of the Gaussian very quickly. So although this is strictly true in the limit of large n, in practice we get to the limiting distribution of the Gaussian in terms of its entropy very quickly. The other point to stress is the entropy going into the system, it simply increases linearly with n, but the entropy of the output goes up as log base 2 of n. And so very quickly you get to the point where almost all the information coming into the system is being lost. And as I say, I'm going to skip past this. There is a movie online. The first of our experimental systems is looking at one of COSA's benchmarks. It's an integer system. The idea is to evolve a program that calculates the Fibonacci sequence. We're going to deliberately have a large population. We're deliberately going to run it for a long time so that not only do we solve the problem, but we also generate large functions. We generate a large function and then we disrupt it. So there are 2 forms of disruption. The first one is we simply take the evaluation of the program and add 1 to its evaluation. So it's an integer system. Adding 1 is the smallest possible disruption. And then we chase through execution of that program with our disruption and see, does it make any difference to the output? The second one is we simply randomize evaluation. So at one point in the program, we just totally replace its answer with a random value. And then again, see where that disruption propagates to, and in particular, does it reach the output of the program? And I'll give away the answer. In almost all cases, neither form of disruption reaches the output. So this is we did this 10 times. This is one of the large programs evolved. The red nodes are points in the program where we can disrupt the output, disrupt the node by adding +1 to it, and it disrupts the output in most test cases. The blue ones it disrupts the output in 1 test case. So it's still a detectable difference. And then the vast majority of the program, the stuff in white, we can add 1 to its evaluation, and it makes no difference on any of the test cases. And here we have, as I said, we did this 10 times, looking at the probability of disruption as we move away from the output. So what I've got going across on the x-axis is the depth of disruption, effectively the distance from the output. And you can see the chance of a disruption making any difference on any of the test cases falls rapidly. In fact, if we look at this next example, it falls exponentially. Dan? Sorry. So in this tree, this is the trees I'm talking about. Depth is simply distance from the root node. The answer pops out of the root node. Effectively, they are function calls. And so as we go through more function calls, as we're further and further from the output node, the chance of a disruption falls exponentially. And this is all in accordance with what you would expect from information theory. So the last part is, well, that's nice, neat, functional programs. What happens in messy C++? As I said, we're going to use Amric's Magpie tool. We're going to use a parsec sequence of benchmarks. These were generated by NASA some time ago for stressing supercomputers. Mostly they're numeric, but there are a few image processing examples. And in particular, we're going to use the VIPS image processing library and the thumbnail application. So it's a very small application. It's about 7,000 lines of, it's about 90,000 lines of code in total. But of those, we're going to allow Magpie to mutate 7,000. So we profile the system beforehand so that we're reasonably confident that the parts that Magpie can see are actually being executed. And then we'll do the same trick again. We'll mutate the code and we'll see if it makes any difference. So the problem is to take the large image on the left and create the thumbnail on the right. And we're going to insist the output is exactly the same. So if you make 1 bit difference to the output, it's regarded as failing. So we did this 1,000 times. In the table, you see at the top, 526, meaning in more than half the cases, the mutant compiled, it ran, and it produced an identical output. There's about 30% of the cases where things fail to compile. There's about 17% where the output was where the program ran, but the output was different in some way. And what I've separated out is the number of cases where the program simply segfaulted or raised some form of exception. And of interest are the 37 cases where the program ran but generated the wrong answer. What I'm going to do as a separate exercise is instrument 25 of those and 25 of the cases where the program ran. The point being to demonstrate that the mutant was actually executed. It did change execution in some way. And then to see which cases that disruption reached the output. And that's what this graph is trying to show. So the blue cases are cases where a Magpie mutant has been executed. It makes a difference. On the y-axis is the number of times it was executed. So this code has been instrumented. We can count the number of times it executes. We can count the depth at which it executes. So some of these mutants actually occur at different depths just because of the way the program is organized. So those are the blue ones. And then the red ones are the same thing, except although the code was disrupted, it makes no difference to the output. So it's entirely undetectable disruption. And the point of the graph is to highlight that above a certain depth, about 30 in this example, the chance of a disruption reaching the output is very low. So there's a big contrast between shallow mutants and deeper ones. Okay, so that's essentially that graph is essentially the message of the talk. Essentially, what I've done is I've gone through information theory to talk about why we should expect failed disruption propagation, why we should expect code to be robust. We see exactly this behavior in pure functions that are generated artificially, but we also see something very similar in real code. So this is code that's been around a long time. It's been generated to solve a problem, not to demonstrate the point I'm making here. In terms of implications, what we should like to be able to do, and maybe in genetic improvement we can do this, is we would like the test oracle to be close to the error. In terms of bug testing, that might mean we actually need many test oracles. This gives a reasoning for why we prefer unit testing over system testing. Unit tests are naturally going to be closer to where the errors are. In terms of system testing, obviously, the errors have to propagate further before they can be measured. Possibly there's an argument for flaky tests, where typically a flaky test the bug may not only have to propagate to the output of a program, but it might also have to propagate between different computers. So potentially, again, there might be more scope for losing information in that process, going from one computer to the other. In terms of software engineering, in terms of software bloat, typically we just measure bloat in terms of extra code size. And what I'm suggesting here is stacking levels of libraries on top of each other might actually be the more important thing to worry about. In terms of software robustness, what we expect is deeper code to be harder to test, to be harder to improve, to optimize, to repair. And as I said, in terms of automatic bug fixing, maybe we've got control. We can change where the mutants happen. It might actually make sense to try and make shallow changes rather than deeper ones, or at any rate, try and put more probes into the system. So again, you might want to artificially add not just mutants, but also add test probes. So at that point, I should stop. Thank you.
Thank you, Bill. Any question from the audience?
Dan.
What were the mutations? Like 1,000 seems like quite a small number, but is it something where it needed recompiling each time fully?
Oh, okay. So the mutations are standard things made by Magpie. They're changes at the level of the AST. So the code is converted to XML. The Magpie mutates the XML, regenerates C++, and attempts to compile it. So there's things like changing constant values, in particular, things like deleting statements, moving statements from one place to another. So the idea is Magpie will respect the tree structure, and mostly mutants will compile. Mostly if they compile, they also execute and run.
Okay, so why 1,000 then? I guess is my question. Like,
It's
why
a
not 10,000?
nice round number.
Okay.
Literally no. So the point being, of those 1,000, most of them run and produce the same answer, but there's sufficient number that fail that you have something to contrast against. So of the 1,000, I think there were something like about 160 failures. So you've got some sort of statistical power looking at failures. And what I actually had to do was instrument the cases of interest. So I could instrument to know what depth they were executing at and verify they really were being executed.
Okay.
Sure.
Continuing the theme of probably now being an old man, I'm reminded of your earlier work with Ricardo Poli about the GP plot. So are we talking about the same thing, just under different shades of GI, or how do you see the relationship between the deep depth here and then how much of that being the plot?
Okay, so for those who don't know, Ricardo and I wrote the book that's floating around somewhere. So as Max is now demonstrating, so we spend a lot of time investigating the theory of how things evolve. And to be honest, that's where this work came from. So, but the point being, having seen that information flow within the GP trees is very important to how they behave. Would the same thing apply in real programs where we have very nested structure, but we also have global variables? So as you would expect in something that's image processing, the central data structure is pretty much shared by virtually all the functions. Yet we see something similar. Is obviously not as clean and clear cut, but the message being what you need to concentrate on is depth rather than size. I think that's an interesting one, particularly in a software engineering context.
Okay, thank you.
I have one question more related to the first example for Fibonacci. You mentioned changing the numbers doesn't propagate to the output. And initially I would think changing a number would always propagate to the top. Do you know why it does not? Or
so I'm going to deflect that slightly and talk about the other example. So there's a floating point example which just does the same thing. And I spent a long time analyzing that, and that is published. But essentially, the reason why it doesn't propagate is rounding error. So you get to the point where the program is sufficiently deep that adding two numbers gets exactly the same answer, even though one of them has been disrupted by a mutation way down the tree. So this is all being done in practical computation. This is all being done in 32-bit arithmetic. And in that case, as I say, I analyzed it in some detail, and there are loads of cases where once something synchronizes in terms of positions within the tree, it remains synchronized all the way through the rest of the computation. And so if you've got 1,000 test cases, maybe you start off with 2 or 3 that are synchronized, but as you go further and further up the tree, you eventually get to the point where all of them are synchronized, at which point in this nested structure, there's no way it can break. And the point of these experiments was to say, well, do we see something similar in C++? It's full of side effects. And the surprise is, well, it's not identical, but it is very similar.
Thanks.
Thank you.
Okay. Is there any question? Well, I have one last question.
Okay.
Can I ask? So I think the fitness sensitivity or disruption sensitivity here is
Gavin,
yeah.
hold it near your mouth.
Okay. Is affected by not only the structure of the source code, but also by the task input. So, for example, having stronger task input can discover previously undetected deep mutations in the source codes. So, considering that, how do you think having stronger task inputs will affect the result in this experiment?
Okay, so there is some work on this. So there was some work done a while ago on Java on defect4j, which was looking at the scope for changing test cases. So in particular, generating more test cases. So this is work with David Clark. And you could see that the impact of disruption was very much concerned with how you were measuring it. So if you had a very strong oracle, then it could pick up comparatively small disruption. Whereas if you had a weak oracle, maybe only a few test cases, then disruption was more likely to be more likely not to reach the output, and more likely not to be observed. So the strength of the oracle is actually very important. So not just how many oracles you have and what depth they are, but also in terms of how well you're testing the code. Thank you.
Okay, thank you.